All right, guys, good afternoon. I am very excited to get us started with a new unit, differential equations. This is probably some of the most fun and most applicable calculus because what this is doing is it's any equation that involves one or more derivatives of a function. And even though you guys talked about exponential growth and change and all these different types of functions when you were in algebra 2 and pre-calculus and algebra 1, here is where they actually all start coming together and become truly real life applicable. So when we are looking at differential equations, it has all of these equations that describe relationships involving rates of change. So rocket science is literally a utilization of differential equations. A lot of engineering fields use differential equations. There's a super great video, 3 Blue, 1 Brown, one of my favorite YouTube channels, that talks about kind of solving and studying the unsolvable and looking at the study of differential equations. If you have some extra time on your hands and you're very curious, I highly recommend it. So the first step in differential equations is writing that derivative piece or that rate of change piece. So on this very first example here, we're going to have a little bit of practice with that, and then I'm going to have you guys pause and go and practice some on Khan Academy. Two key things to note is that we have two separate relationships that you'll normally see. You'll either see directly proportional or inversely proportional. Most of the time when we see the keywords inversely, we're going to have some sort of a fractional rate, or you're going to be having right, because inversely means they're on opposite sides. They're inverses, where direct proportional means this rate is moving at the exact same rate as the other one. So our first example says, Alex and Tina have a new Maine Coon kitten, oh my goodness, named King Robert. Robert is gaining weight, W, at a rate that is inversely proportional to his age, T, in months. So what I'm going to do, since we're talking about the rate of his weight, we're going to call this dW over dt. After I have that dW over dt, it's inversely proportional to his age in months. Inverse, right, if things are inverses of each other, that's that 1 over. So this W, since this guy's in the numerator, his age, it needs to be in the denominator on the other side. The other thing that we have here is we have this constant k who comes into the numerator. I don't know what that constant is, and I also want for this to be an equation that works for any age in months, any weight, and then also any kind of constant of proportionality. So we use this k here as just an unknown value so that we can apply it to any scenario. Part B, your cup of Starbites peppermint coffee is cooling at a rate that is proportional to the difference between the room temperature, TR, and the current temperature, T, of the coffee. So let's get that first piece taken care of. We know that we're going to have one piece is the difference between the room temperature and the current temperature. I'm going to call this T minus TR. The difference between the room temperature and the current. Then I know that your cup is cooling, so the rate of change of my cup, which would be that dt over d smaller t, capital T, the rate of change of that cup, it is directly proportional, so we don't have a fraction. We still need that constant of proportionality. So when it's inversely proportional, that constant is divided by that inversely proportional piece. When it's directly proportional, we're multiplying that constant. And then the last bit of information is checking the sign of that constant. Because my coffee is cooling, I'm going to put a negative k value right here because I know this is negative or k is less than 0 because temp is decreasing. Take a second and go and get this Khan Academy taken care of. That link should be on that side of that Edpuzzle. And once you are feeling good about getting 3 out of 4 or 4 out of 4, come back for a few more notes. All right, now that you guys are back, we're going to talk about verifying solutions for differential equations. So the first step is kind of being able to write those pieces. We'll look more into that when you guys get back to class, and we're going to be solving some real world. But the next piece of it is talking about like those solutions to these differential equations. Most of the time, we of course have specific solutions, but a lot of the time we have these general solutions because the whole idea is that solutions to our differential equations, we don't want to just like pigeonhole it to one value. We want to say like, oh, if I'm looking for it at this time or at this value, I have general types of equations that can do that for everything. So the general solution of a first-order differential equation represents the family of curves, and we're going to investigate that when we start drawing slope fields, very exciting things. But first, I want for you guys to look at some of the notation for representing differential equations, and note that these are all proper notation, and you guys have seen these before. We see the dy over dx, we see the f prime, we see the y prime. These all work. Okay, let's look at this first example. So what differential equations do is we look at different parts of rates of change. So if we look and we see like, oh, a first rate of change and a second rate of change satisfy this equation, right? And that's what we're showing in all these different examples. So when we are looking for valid solutions, it is important that we are first off able to differentiate quickly. Second, that we are able to check and plug it into the original. So we're going to be showing that both y equals 2e to the x and y equals e to the negative 4x. Are these both valid solutions for the differential equation y double prime plus 3y prime equals 4y? This seems like a mouthful. I'm going to split this up into two pieces though. And we're going to first deal with y equals 2e to the x, and then we're going to deal with y equals e to the negative 4x. Since I'm looking to substitute them into this equation here, for both of these equations, I need y prime and y double prime. On this first equation, y prime is going to be 2e to the x. Y double prime is also 2e to the x. On this next equation, we have a little bit difference going on because we do have a chain rule applying here. Y prime is negative 4e to the negative 4x, and then y double prime is going to be 16e to the negative 4x. So I'm checking that these are going to be solutions. So what we're saying is that y double prime plus 3 times y prime, does that equal 4 times y? And now I'm going to start with some substitution. We'll get some color coding here. So there's your y value. We are plugging this guy in. We are checking for equivalency. Your y prime gets substituted and multiplied by 3. And then your y double prime is that first term. So let's get those subbed in and check. Are these both valid solutions? So if I have 2e to the x plus 3 times 2e to the x, does that equal 4 times 2e to the x? 6, 7, 8, so I have 8e to the x. Does that equal, 8e to the x? It does, so yes, valid solutions. On this next guy right here, we have 16e to the negative 4x. Negative e to the 4x, does that equal 4 times e to the negative 4x? Negative. So negative 12 and 16, we know that that is going to be 4e to the negative 4x. And does that equal 4e to the negative 4x? Indeed it does. So yes, valid solutions. This is not always true. This is just kind of like the method for checking. So go to this Khan Academy and finish this before we go to class, and you will notice that sometimes, yes, we do have solutions. Sometimes, no, they are not solutions, but you do have to methodically check them by differentiating and then substituting into the differential equation that is given. I'll see you guys tomorrow.